Welcome, everybody, and thank you for coming. Thank you for the DHI people for coming downstairs to see CMSA. So, yeah, we've been thinking that it would be a good idea to have some joint meetings to bring together anyone working on black hole stuff. So that will be the first meeting, and we'll see how it goes. Hopefully, it will attract many people from around the campus. So it's a pleasure to have today Matthew Dodelson as our first speaker. Matthew did his PhD in Stanford under Eva Silverstein, and then postdocs at IPNU, right, in Japan, and at CERN, and he joined the physics department here at Harvard recently. So it's a pleasure to have Matthew, and take it from here, Matthew. Thank you.
Well, thanks for the nice introduction, to the invitation. I'm not going to be telling you about black holes, but I'm going to be telling you about some analog of black holes in quantum systems. So hopefully this is close enough to what you folks think about that it'll be vaguely understandable. So we're going to see that there's some analog of quasi-normal modes in quantum systems at finite temperature. And here's a quick outline. So I'll tell you how quasi-normal modes encode the geometry of black holes. So that will be a review. Then I'll tell you how to compute them in quantum systems. And in particular, we want to see how the error of time emerges in the quantum system. And finally, I'll give an example that I discussed in this paper, where these quasi-normal modes can be very easily computed in the SYK model. I should say that because it's more of a broad audience, I tried to make it less technical, but it's still going to be technical. So if you want me to slow down, please say so. Yeah. So I'm interested in quantum systems at finite temperature. And in particular, I want the entropy of the system to be infinite. So you can think of a spin system on a lattice in the limit of infinite volume, or you can think of a system with an infinite number of local degrees of freedom, like a large N gauge theory. And the quantity that I want to discuss is the correlation function at finite temperature, which is defined like this. So here, O is some operator in the theory. Beta is the inverse temperature, and this is how you compute the correlation function. And in a system with infinite entropy, we expect that at late times, this quantity thermalizes. So what that means is that CFT goes to 0. Okay. And the question is, how does it go to 0? Is it exponential? Is it power law? Is it exponential times the power law? Is it something much more complicated? And one very simple option is that it's just a sum of exponentials. Now we want it to go to 0 at late times. So what this says is that the imaginary part of omega n is less than 0. So these are complex frequencies, and the system eventually rings down into thermal equilibrium. So I'll call this ring down behavior. And many of you are familiar with its behavior in a very different context, which is black hole mergers, because at very late times, after the two black holes merge, you have a ring down that's exactly like this, and the omega n's are the quasi-normal modes of the final black hole.
But is it special to infinite entropy or any? I think even at finite entropy, you have some ring down or some decay.
Well, for a certain amount of time, but then eventually unitarity will make it come back up. So in a finite n system. Okay.
You're probably thinking of entropy density versus entropy.
Yeah.
We're talking about total entropy.
Yeah. So if you have a spin chain with a finite number of sites, it'll eventually recur. Any other questions about this? Okay, so I made some vague analogy between this exponential decay and black holes. But this analogy is actually very precise in a certain limit. So this is made precise in ADS-CFT.
Quick question.
Yes.
I'm a little confused. How can the analogy be so precise when your premise is infinite entropy? That is not the case, right, for black holes? I'm a little confused.
Yeah, so it is the case in the limit where G Newton goes to 0, right? Because the entropy is the area over 4 G Newton. Yeah.
Okay. Okay, so the limit, yes. Okay.
Right, so that's the limit that I'll be discussing
Okay.
here.
Thanks.
Thank you for the question.
Yeah, I missed that. Yeah.
So this is made precise in something called ADS-TFT. Which I'll just give you a brief overview of how this works. So in ADS-CFT, the quantum field theory in d dimensions is equivalent to a gravitational theory in d+1 dimensions. Okay. So in this case, the quantum field theory will be this quantum system, and then it's mapped to a gravitational theory. We have a number n, which is roughly speaking the number of local degrees of freedom. And this is going to be mapped to 1 over G Newton. So the limit n goes to infinity is the limit where G Newton goes to 0, which is the limit where gravitational loops are very small. So this is the classical limit. 1 to infinity is classical. Okay. There's also a coupling constant in the in this quantum system, which I'll call lambda. And lambda is going to map to a scale that measures the non-locality of the gravitational theory. And in particular, this is some string theory, and the string length is alpha prime, and a very strong couple in lambda. Alpha prime goes to 0, and so instead of string theory, we just have local quantum field theory in this gravitational theory. Okay. Next, we're interested in thermal physics, and the thermal state maps to a black hole in this gravitational theory. And finally, these omega n's map to the quasi-normal modes of the black hole. Okay, so this reduces the problem of computing these omega n's to computing solutions to the wave equation in this black hole background. So
That's alpha prime is the string length,
yeah.
and it's prime because that's just notation. Okay, and the gravity theory, the black holes that we're talking about are anti-de Sitter.
Yeah, alpha is taken by the QD 1 over 137. So it's alpha prime. Yeah.
How does the spin of the perturbation on the gravity side enter the quantum field side?
Yeah, so so I wasn't specific about the operators here, but they're also a function of position, Fourier transform into the spin basis. And, yeah. Any other questions? Okay, so now let me tell you the answer for these omega n's. I'll tell you everything we know about these omega n's in a particular quantum system, which has this holographic description. So let me take the Fourier transform. And I'll define C of omega. Like this. So now you see that these omega n's map to poles of C of omega. And so we can plot the complex omega plane. And I'll start with lambda equals infinity. So this is the limit where we don't have string theory. It's the strong coupling limit on the boundary. And here's the answer. So we have these quasi-normal modes, and they're discrete, like this. And they form a tree-like structure. So this is sometimes called the Christmas tree, because it looks like a Christmas tree. Okay, and again, this is the complex omega plane. So that's the strong coupling limit of this gauge theory. And it has this very simple form. Now, the other limit in which we can do computations.
So is it fair to say that this is actually computed using the black hole?
Absolutely.
It's not computed in the gauge theory at all.
Absolutely. Yeah, so we don't know how to do the computation in the gauge theory, but we know this amazing duality that lets us do the computation anyway. So the other limit in which we can more easily do the computation is lambda equals 0. So this is a free field theory. So here you can imagine you can do the computation. And what you find is very different. So instead of these discrete poles, you find branch cuts. So again, this is the omega plane. So there's some tension here, right? It looks very different. Yeah.
Is it the general discussion at anything, or are you referring specifically?
So here, if you do it NED, the angle changes, but the picture looks similar.
So far the discussion is general.
No.
So-
To some extent, yeah.
So it's in 2 dimensions, or?
So this picture is it looks like this in 4 boundary dimensions. So n equals 4.
So we should think about n equals 4 and ideas 5 so far?
Yeah. So this picture was done in n equals 4 at 0 couple.
The branch cuts go all the way minus v to infinity, right? Or they-
So here the operators are labeled by a spatial momentum.
Right, okay.
And it's at infinite volume, so this spatial momentum is k, and the branch cuts stretch from a minus k to plus k. So the k is now of the spin at infinite volume. And the question I want to ask is, we have this nice picture at lambda equals infinity. We have this nice picture at lambda equals 0. What happens in between? Because they look very different. And in particular, are there poles? Are there cuts? Are there poles and cuts? So this is an open question that I want to address. So what's the bulk picture at finite lambda? Well, I told you that the string scale is now finite. So this is what I'll call a stringy black hole. So it's some very non-local geometry, but it's still classical because G Newton is just still very small. And we want to study its geometry, but we don't have to do that in terms of a metric and classical fields. So what I'll do is just study the spectrum of quasi-normal modes. You hit it with a perturbation, and you see how it breaks down.
And this is computed using the field theory?
Yeah, we're going to do an estimate. Yeah, so we can't do this computation in n equals 4 segregating mills or in any theory in higher dimensions, but we can do it in this SYK model, and that's where we're going to go. Any questions? Okay. So I want to review. When did I start? So I want to now review the quasi-normal modes and see how they encode the black hole geometry. And then we can hope that if we can compute them at finite lambda, it'll tell us something about the stringy black hole geometry. But first, let me take lambda equals infinity. So strings decouple, it's purely gravity, and we want to see how the geometry is encoded in these quasi-normals. So at infinite lambda, we have a classical wave equation. And this is the wave equation for perturbations on the ADS black hole. So there's a very similar wave equation in asymptotic black holes, and here we want to analyze it in this case. So R goes to infinity is the ADS boundary. ADS is a spacetime that has a boundary. And R goes to 0 is the black hole singularity. Okay. And then there's a horizon at R equals RH. And what a quasi-normal mode is a normalizable ingoing solution. So a normalizable means that it falls off fast enough near the ADS boundary, and ingoing means at the horizon it's purely ingoing. So you would make a very similar definition in asymptotic flat black holes, but the boundary conditions at infinity are slightly different. Okay, so I'm going to tell you a few examples of these quasi-normal modes, and I'm going to tell you how they encode the black hole geometry. So the first example is this Christmas tree. So let me take an ADS5 black brain. So what this is, it's an infinitely large black hole, and it's dual to the boundary theory at infinite volume. So it's dual to a conformal field theory on R4 times the thermal circle. Okay, so here's the potential. So what you do is you have some metric, and now you compute the potential, and it looks like this. So it's a monotonic potential, BR, and it blows up at the singularity, and it blows up at the boundary. And for the quasi-normals, you find this picture, which I drew before. The omega plan. Okay. So what I want to point out is that there's two interesting limits you can take. You can take omega goes to plus infinity, so you can go out here, or you can take omega goes to minus I infinity. So this limit is very natural. You're just going to high energies. This is some very strange limit where you analytically continue the energy to complex frequencies, and then you take some asymptotic limit. So this is very unnatural from the point of view of the boundary, but it's very interesting because what it does is probe the black hole singularity. So let me explain that a bit. So
R equals 0, there's a horizon, not the singularity.
So this is the horizon.
Oh, sorry.
Yeah, so it blows up, yeah. Any other question?
But it's so only outside the horizon, right?
Yeah,
So, okay, so we don't have to.
yeah, so it's gonna, yeah, so that's why you need to analytically continue. It's a bit technical, but
What was the question?
sorry.
So what was the question?
The question was,
It's so only outside the horizon, so.
It's a wave equation that's only outside the horizon, so the question was how can it probe this the black hole singularity? So I'll first tell you why, and then I'll answer your question.
Also, you solve for the spectrum numerically?
Yeah, you can do it numerically. You can do it analytically at large Moore number. Yeah. Okay, so I want to explain a little bit about why this probes the black hole singularity. So suppose we look for a turning point in the WKB approximation. So a turning point is when the potential is equal to omega squared. Omega is the energy. So there's two ways to get very high energy. So if we look at this picture, one way that we can get very high energy is to take R goes to infinity, which is the boundary. Okay, yes. So at very large R, this potential blows up, and so that's one way to get omega goes to infinity. And here omega goes to plus infinity. So this very natural limit of large energies is going to probe the boundary of ADS. The other very subtle limit is we can take R goes to 0 because you can see that the potential is blowing up there. But now it's negative. So the potential is negative. And so what this tells you is that omega goes to minus I infinity is what's being probed. And so this subtle asymptotic limit is probing the black hole singularity. So let me say a little more. So if we draw the Penrose diagram, it looks like this. We have the black hole horizon, we have the black hole singularity, we have the boundary of ADS, and we can draw geodesics that go from one side to the other. And these give some contribution to the 2-point function. And the turning point here, it goes to the singularity in this limit, omega goes to minus I infinity. So this limit is probing this geodesic. And yes.
No, I'm just a little bit confused. Aren't you solving only outside?
Yeah, I'm going to answer your question. Yeah. So,
Sorry, can you come out of the black hole?
okay.
Geodesics, I thought were into the same way.
So this is a space-time geodesic.
Okay.
So I'll tell you one more thing and then I'll answer this question. So at large imaginary frequencies, you find exponential decay of the Green's function. So this I'll just tell you. So this is the answer that comes from this geodesic. Okay, so now for his question, which has a technical answer. It's true, we're solving the wave equation outside the black hole horizon, so we never really prove the black hole singularity. But what's been being done here is to analytically continue in frequency. And then in WKB, you have to analytically continue the metric also. So
Yeah, it means that you can map the solution outside and solution inside.
you can analytically continue in the metric.
Struggling with this a little bit.
Yes.
So the interior of the black hole is going to be some non-stationary spacetime, right? So how do you find, what is the meaning of, like the structure of the Minkowski equation will itself change? It'll be some different equation. Because a time-dependent metric. So
You mean time dependent because it depends on R or?
It's not clear.
Yeah.
It's not that.
but even in Schwarzschild, for example, or EDS, you would have some time, like because T and R switch carry time like equilibrate. Right? So what is the meaning then of a quasi-normal mode? Like, does that the same? Like in cosmology, would you be able to, in a cosmological space-time, would you still be able to write down the same sort of quasi-normal mode frequency?
Yes, well, what I'm doing here is a trick to compute the quasi-normal ordinary quasi,
Right.
and it involves analytically continuing to the interior. Okay. There's no independent definition of the interior.
So you said you're also complexifying the space-time?
Yeah.
With the interior. What does that mean? Is the interior geometry the same?
Yeah. So I just study the maximal analytic continuation of this
Right.
of the exterior, and that's the ordinary thing that you know. Any other questions about this example? Okay, I'll tell you one more example because it might be of interest to some of you. So another example, you can ask, how do you see the black hole photon sphere? So this example was meant to address the question, how you see the black hole singularity in the quasi-normal modes. And now I want to ask, how do you see the black hole photon sphere? So in this case, if you draw the potential, now it's a function of angular momentum. And the potential at large angular momentum looks like this. So before it was monotonic, and now it has an unstable maximum. So this is called the photon sphere. And in the spectrum of quasi-normal modes, what you find, up to some technicalities, which I'll explain in a second, is the following. So this might be familiar to you as the iconal spectrum of quasi-normal modes. Omega is the frequency on the photon sphere. Sorry, the velocity of null geodesics on the photon sphere, and gamma is called the Lyapunov exponent. So this is what they're trying to measure. So
Sorry, what does that say? I just can't read the.
I'm sorry. So this is omega times L, m plus 1/2 times gamma, and gamma is called the Lyapunov exponent.
And that's in the iconal, right? It's not the.
Yeah. So I'll not tell you the limit. So it's a very strange limit that you have to take. It's L goes to I infinity. So this is the limit in which you can see the iconal spectrum. L goes to plus infinity is much more subtle. But you can recover this usual flat space analog in the limit of large imaginary space.
But in asymptotic flat, it would be L equal to infinity, right?
Yeah,
Something like that.
yeah. So in asymptotic flat, you could go in any direction in the complex plane you want. Yeah. So L goes to plus infinity or L goes to infinity. Both have yes.
So how would you characterize the absence of the photon sphere or photon plane in the black brain? So is it the statement that if you take L goes to I infinity, you don't find how would you say that the black brain does not have a photon sphere?
So you would say, so notice that this has quasi-normal modes that have the imaginary part of omega n is greater than the imaginary part of L. Because omega is bigger than 1. And in the black brain, this cannot happen. Any other questions before we move to the boundary? So the whole point of this was to give examples of how these quasi-normal modes, which are purely boundary quantities, how you can see geometry through them. So now we can try to compute them in one. Yes.
So this R going to 0 limit.
Yeah.
Is this specific to radius or it also is in asymptotic black hole space time?
It's working. Is it safe to say that you can also see it in flat space?
So in flat space, you see the same spectrum but real L. You take real L goes to plus infinity, you get a spectrum that looks different.
Okay, good. Any other questions? We're about halfway through, so now it's a good time to explore the other side of the duality. Okay, good. So we want to compute quasi-normal modes in this quantum system, and what we'll get from our computation is the correlation function in perturbation theory. So we have some coupling constant J, and we're going to do perturbation theory, and this is going to converge up to a time which is finite. So this function has a finite radius of convergence in time. But we can compute it very, very well up to this time t star. And now what we want to do is to fit to a sum of exponentials. But this is the problem we have to solve. So I want to point something out here. So this almost looks like non-unitary time evolution. So if these frequencies have imaginary part, which is less than 0. So if these were real frequencies, we would think, oh, this is unitary time evolution with real energies. But here we have imaginary frequencies, so it looks non-unitary. And so the question is, how do these non-unitary dynamics arise from a system that is purely actually unitary? And this is the problem of the arrow of time.
It's because of the boundary conditions, right?
So remember, we're on the boundary. So there's no. So this is in the boundary theory. So everything.
Yeah. So from the gravity,
From the
you can impose boundary conditions that are not Hermitian and then.
Yeah. So that's the bulk interpretation. But here we're working purely on the boundary. And so what I'm going to do is I'm going to define an operator U tilde, which is a modified time evolution operator, and the eigenvalues of this operator are going to map to these complex frequencies. So we can get dynamics that look non-unitary or dissipative from underlying unitary dynamics. So there's a nice trick for doing this, and it's naturally going to come out of this problem of exponential fitting. So I'm going to tell you how to fit to sum of exponentials. This is a problem that's very familiar from chemistry, for instance. In chemistry, they often have a very short time signal for the correlation function, and they want to extract all these resonances from this signal. And they use the technique that I'll now tell you. So the idea is we truncate to a finite number of exponentials, and we solve these equations. So here J goes from 0 to 2s minus 1, and s is our upper cutoff. So we have two s unknowns, which are these dn's and the omega n's, and we have two s equations. So that's enough equations for the number of unknowns that we have. So what we're doing is solving this equation on a grid.
You put a lower cutoff on pi?
If you wanted to, but in our case, it's non-singular at t.
So is your omega n now real, or is it still complex?
Omega n's are still complex.
Complex. I thought you were counting it as 1 for each frequency.
Let's say again.
When you were saying, you got two unknowns, dn and omega n.
Sorry, I meant 2s complex unknowns.
2s complex. Yeah. Oh, okay. You've got 2s plus 1.
Exactly.
Minus 1 there. Yeah, okay. I see.
Any other questions? Yeah, so what this is doing is we have this signal which we know of T star, and then it's solving these equations on a finite grid. And then hopefully we can take S goes to infinity and it will converge. So here's how you solve this equation. So I'm going to introduce a little bit of notation. So I'm going to have a Hilbert space of operators, O, and the inner product on this Hilbert space is going to be like this. So this is appropriate for infinite temperature, beta equals 0, which is where I will do my computations. So now I'm going to look for my U tilde operators. So remember, this is the operator that was related to these complex eigenvalues. And my ansatz is going to be this. So I want this operator to satisfy this identity. So this is C of j times delta t, which is this quantity, and this is the jth power of the jth power of U tilde. And you can see what happens, because if you have this equation, we compare this side with this side, and we see that the eigenvalues of U tilde are just these omega f's. And in particular, we have the following eigenvector equation. So U tilde is a finite dimensional operator, and it has S eigenvalues. And these are the eigenvalues. Does this make sense? Okay, so now we're going to solve for these eigenvalues. So the way to do this is to make an ansatz for the eigenvector, and it's a very simple ansatz. So we just take our operator U tilde and we just time evolve by these discrete times. And this is a linear combination of J vectors. So that's our ansatz. And if you plug this into this equation, what you find is a generalized eigenvalue equation for these B's. And it looks like this. And M0 and M1 are just made out of this correlator. So what I'm telling you is, if you know the correlator at all the points on this grid, you can form these matrices, right? And then you can solve this generalized eigenvalue equation, and then you can compute the omega f's. Does this procedure make any sense?
So these eigenvectors, are they an orthogonal basis or?
They are not, because it's non-unitary. Yeah, they're.
Oh, okay.
Yeah, there's left and right eigenvectors. Okay. Okay, so you can solve this eigenvector equation purely from knowing the correlator up to a finite time, and then you get an approximation to the correlation function with S eigenvalues. And now we take S goes to infinity. And we hope for the best. We hope for convergence. If it doesn't converge, if we have some accumulation of eigenvalues, then it just tells us that our initial assumption was wrong. So this is an assumption. We can't derive that there are quasi-normal modes or these exponentials. But if it's correct, if this is true, then this procedure will give convergence. Yes.
So you're taking S to infinity, but keeping T star constant?
Exactly.
Okay,
So we take delta T goes to 0.
just makes it.
Okay, so this is how the arrow of time, which is non-unitary dynamics, emerges from an underlying unitary theory. And a similar thing happens in classically chaotic systems. You have this time evolution operator, and you coarse grain it to get these complex eigenvalues, which are called the Ruel resonances. And yeah, so this is a very general method for computing resonances in systems. Any more questions about that?
So the conclusion, so you coarse grain this,
Yeah.
you solve for the eigenvectors
Yeah.
on the boundary, and then, but what's this, can you just say the punchline again about why this gives you the arrow of time? How do you get out of the unitary reversibility of time?
Yeah, so the important thing is that the spectrum of real eigenvalues is continuous. So the entropy is infinite. So you can make these you can write the correlation function as either an integral over a continuous set of frequencies or over a discrete set of eigenvalues. So there's two equivalent descriptions, and I think one way of saying this is, at least in these classically chaotic systems, the eigenvectors for this U tilde live in an extended Hilbert space. Yeah. So they don't live in the ordinary function space. More questions? Okay, so now let's do it. So now we want to fix a particular theory. And we want a theory in which we can compute things very well. And
Matthew, just before you erase that.
yes,
So I have a very nice question.
yes,
So let's suppose you have a quantum system which is unitary. It does not display these properties. Like it doesn't. It remains unitary.
yes,
Essentially, what would the correlation function look like? Would it just be oscillatory?
yeah,
Okay. So as soon as you see something that's decaying like this,
Yeah.
you know that there are some complex frequencies in your spectrum.
well, so not necessarily, right? It could decay like a parallel.
Okay.
So this is a very specific situation.
I see.
Yeah.
So if it decays in some specific way, you get these this nice Poisson mode interpretation.
Yeah,
But independent of this particular Poisson mode interpretation, if you see a decaying correlation function, do you know that you have this arrow of time behavior?
yeah, I think you would say that you have some dissipation. So for instance, if you have hydrodynamics with very almost conserved operators, those decay slower. So those decay like a parallel. So we want to.
I would say parallel is special, right? It's an indication of some performance symmetry.
Let's say
The parallel is an indication of performance symmetry.
I don't think so. In a hydrodynamics situation, a very long
Dynamics.
So if you take a conformal field theory, it's parallel at zero temperature. These correlations at finite temperature, even a CFP has to be.
Okay, so I'm going to write down a model in which we can do computations very accurately. So this is called the SYK model, Sachdev, Yi, and Kitai. And it's a model of n fermions, and it's just a quantum mechanics. So there's an interaction potential which involves Q fermions. So here's the Hamiltonian. So it's a sum. Oops. Be very careful, because experts in the audience. See if I get it right. Okay, it's good. So we have n fermions, and they interact with each other via this Q body potential, and this is a model of 0 + 1 dimensional quantum mechanics. It's very simple. And what you should do after computing things is to average over these couplings J. And J should have an average which scales in a particular way with n. And what you find is a very simple perturbative expansion. So let me take 2 = 4. So if you compute the 2-point volume of the propagator, this is equal to the free answer plus this 4-body interaction plus higher body interactions. Okay.
Sorry, actually.
See what you get. I guess you know this already. Okay. So now what happens is only certain diagrams contribute, and it's diagrams that look like this. So you can draw a loop here, a loop here, a loop here. So it's a very simple subset of diagrams, and you can write down a consistency equation. Oops, what am I doing? So this notation means you take the exact propagator, and then you have higher 2pi contributions, and then it keeps going. So this is a consistency equation called the Dodelson equation, and you can put it on a computer, and so you can solve this to any order you like. So because we need very high precision, it's good to compute COT as precisely as we can. And so I did it on a laptop for 2 months, and you can get 10 to the minus 1200 precision. So I'm sure you're laughing, but we need all this precision.
Okay.
So the reason you need it is because we're trying to probe quasi-normal modes that are deep in the complex plane. And those behave like this, e to the minus I omega nt. So let's say the imaginary part is of order 10. So then this is e to the minus 10t. So it just immediately gets killed. And so we better have really good precision. And here's the answer. So this is Q = 4. And we find this nice discrete spectrum of modes. So this was the Christmas tree that I told you about. Remember? So this was the case for the 80th black brane. And then we find modes inside also. Okay. And they're kind of random. So it looks a little bit like a black hole, like an 80th black hole, even though we're not in the holographic regime.
But these extra modes are finite in effect, so.
So this is all infinite n.
Finite lambda.
Exactly. Finite.
So, but I thought that But in the black hole picture, they're not supposed to be there, or
So the,
how are we supposed to think?
yeah, so this is no longer a holographic theory, it's a stringy black hole. Lambda is finite. So the question is not why are these extra modes here? The question is why does it look? There's no reason to have any properties of a black hole. So the surprise is that it does.
And you see that the edges look exactly how I see it.
Okay, so let me just put down some similar properties here. The first one is that it's metamorphic. So what I mean by that is that it has a discrete spectrum of quasi-normals. There's no cuts. And in particular, as I take it, S goes to infinity, I don't see any accumulation points. I just see new modes coming in down here. So this was S equals 670 is as high as you can take it. And up until here, it's all converged up to 4 digits. This one has like 40 digits, but there's no accumulation of cuts or anything. So that's a very black hole-like situation. The second property is it has this tree structure. So the edges of the spectrum look like this black hole.
Does it matter what you choose your string length to be?
So here, that's not a parameter.
Ah, okay.
So here, I have no dimensional parameters, but I have no dimensionless parameters. The analog of the string length is going to be the temperature in units of the coupling. This picture is beta equals 0. So at very low temperatures, there is a holographic description, but this isn't in the opposite. And then the third property, I told you to remember that the signature of the black hole singularity was this exponential decay at omega equals minus I infinity. And another way to say that is that the residues, dn, which are the coefficients of each of the minus I omega and t, these should decay exponentially. So this is true in a holographic theory, and it's also true here. So you find these very black hole-like situations in a case where we didn't really expect it. So that's the surprise. You can do other things. So there's a sense in which if you take Q goes to infinity.
So Matthew, this third point,
Yeah.
that means that the higher frequency Poisson modes are not going to be that important.
Exactly.
So similar to normal gravitational wave stuff. Okay.
Yeah. Let me think. In those cases, I don't think they exponentially decay, but I think that they are smaller.
Yeah, it's the amplitude is typically. I don't know about the exponential decay.
So you can take this Q goes to infinity limit, and in this limit, there's a sense in which the bulk, in which the string length goes to 0. So this is kind of like a lambda equals infinity limit, and you find a spectrum all on the imaginary axis. And so this, sorry. There's this transition from this spectrum to this spectrum. You can model this by taking an ADS2. I guess well, I'll just say this. So this is the redshift factor for ADS2, which has no black hole singularity. You can get this spectrum in that geometry. And then if you add a small perturbation, or mu is small, you find that it mimics this transition from purely imaginary modes to this Christmas tree. So introducing a black hole singularity, it corresponds to this spectrum opening up. Okay, so that's all I wanted to say. So let me conclude. I've kind of tried to argue that you can see signatures of black hole geometry in quantum systems where there's no black hole. And I've told you how to see features of the geometry like black hole singularity or the photon sphere in the spectrum of quasi-normal, and then I've computed it in a certain model. So this is the only example I know of this situation. So in the future, it would be nice to compute spectra of other quantum systems and see if there's some dual black hole geometric interpretation. And the goal is like something like large N QCD or large N being Mills theory. Is there some dual black hole interpretation at finite coupling, and how do we interpret that? Okay, thanks.
Also, when you were asking for finite alpha, for finite lambda.
Yeah.
Whether you would get the discrete or the continuum.
Yeah.
So in this model, what is the answer, that it stays discrete?
Yeah. So I guess my thought, my conjecture, which I don't really have any evidence for, but the conjecture is that in this Yang-Mills theory, there's poles at any finite coupling when the theory is chaotic, and then in the free limit, these poles condense into cones. I have no idea how to show that.
My question was the same, but I'm not able to figure out how this fellow becomes a branch cut. Yeah, so.
Yeah. So in this, so let me. So the picture I'm imagining in the Yang-Mills cases, we just have very finely spaced poles, and then in the limit where lambda goes to 0, these condense. There's not really an analog of the free field limit in this SYK model, which is why I couldn't really study that question.
Right. But you think that a dense collection of poles will just look like a branch cut?
Exactly, yeah. So you imagine a function like sum of dn omega minus omega n goes into an integral of t of omega minus omega n plus I epsilon. And then if you take the discontinuity, so then this is a branch cut that has discontinuity equal to d of omega. So the discontinuity becomes the residue.
Is there any interpretation of the surprising result that it looks like a black hole, or do you think that it will generalize to other theories? Maybe it's a special property of the SYK, or
It could be. Yeah, we don't really know. I think maybe my guess is that it's generic, because whenever we compute it, we see that.
what do you mean whenever?
This is the only example. And in a whole lot of also.
But in a lot of, yeah, it sounds like a holographic property, but
Yeah, I mean, there's a theorem about classical black holes that singularities are generic. Maybe this is a quantum analog. Trees are generic.
any other questions?
So what does the description mean for the boundary theory? What is it said like?
Yeah, so the idea
Is it a statement about the states, the transition between states, or is it about the structure of the theory itself?
Yeah, so the idea is you have a thermal system, you hit it at some time,
Right.
and then that perturbation, scrambled into the thermal bath. So then you measure it at some later time, and you forgot all about the initial
So
perturbation.
at all times, were you keeping the entropy fixed
Entropy is infinite.
infinite, right?
Yeah. If you have finite entropy, then you have Poincare recurrences.
If you connect the dots, they connect to the origin, or
Could you say again?
if you connect the dots along the Christmas tree, do they go into the origin or do they go a little off?
They go off.
Okay, so if there are no more questions, let us thank Matthew again.